Thank you very much for attending. The talk today is titled The Rationale for Continuous Delivery, and what I'd like to talk about is it's my argument that the majority of people that work in the software development industry haven't seen what a good software project looks like, and that's quite a frightening idea. If I'm right, it means that it leads us to making different kinds of decisions. One of the scary things is that I believe that good software projects look quite significantly different to the norm, and I hope that this presentation today is going to convince you that I'm right and that there are ways of looking at this stuff and differently and taking different approaches. So, sorry, right. So if we look at the history of software development, it tends not to be good. We look at sorry, I'm having trouble with my with the controls of my presentation. It's not. Let me just. Right. Okay. Thank you. I've got something that works now. Right. So if we look at project surveys over time, they tend to report a lot of problems with software projects. This last one is a study of 5,400 large-scale projects. 17% of those projects go so badly that they threaten the existence of the company performing them. So I would argue that the state of software development has been, at best, somewhat suboptimal. We're not really doing we're not really performing as well as we could. But I think that there's also signs of optimism. I think there's signs of change. We haven't got it perfectly right yet, but I think that we now know pretty definitively what works. And I hope that the rest of this presentation is going to describe some of that and convince you of it. So what have we tried over the years? So we've looked at other industries, and we've tried to figure out how to take learnings from them and adopt some of the learnings. So we tried things like waterfall processes, V models, throwing change between different parts of organizations, working in silos. We've tried working more iteratively. Over recent years, we've kind of looked at Scrum and started adopting more team-based iterative approaches. We've looked at extreme programming. We've looked at hiring smart people and putting them in a corner. We've looked at hiring young smart people and putting them in a corner because they're cheaper. And we've looked at hiring young smart people in foreign countries because they're even cheaper. And all of these things kind of play a role in our ability to deliver software, but none of them are really the answer. I want to show you a series of pictures, and you can see here that there's a problem. There's a car has fallen off this quayside into the water on the west coast of Ireland. So what do you do in this situation? Well, fairly obviously you get hold of a crane and try and lift the car out. But oops, things can go wrong. So what do you do now? You get a bigger crane. We've got the car out, now we need to get the first crane out of the water, and oops, things still go wrong, so what do we do again? Einstein said that insanity is doing the same thing over and over again and expecting different results. So what is it that we're really looking? What is it that we really want from our software development processes? I would argue that it's true for any organization that produces software. What we're really looking for is we want to have an idea, we want to get that idea in the form of working software into the hands of our users, and we want to figure out what they make of it. And I think that's true of every organization that creates software. So I want to pose a question. What's the most successful invention in human history? And here are some of my suggestions. I would argue without much fear of contradiction that it's actually science. And by this, what I mean is not space shuttles and large hadron colliders. What I mean is the simple process of evaluating ideas and figuring out which ideas work and which ones don't. The empirical Aristotelian approach to science. So like most good presenters, I went and looked it up on Wikipedia, and this is how Wikipedia defines the scientific method. So we want to make a guess based on experience and observation. We want to propose an explanation. We want to make a prediction from that hypothesis, and we want to test the prediction, and we want to repeat. We want to build on our learning. We want to be able to divide up the risk of our approach to solving problems into small chunks so that each one is survivable and survivable. We actually learn more when our experiments go wrong. And so working in small iterative approach, small experimental approach gives us more opportunity for learning. So let's look at some more data. So this is data on software projects from the Chaos Manifesto, which is a report published by the Standish Group, and they've been publishing this report for some years. And on the whole, Agile projects do a bit better than waterfall projects. Waterfall projects tend to have a lower success rate. By success, what we're talking about here is that the projects are on time, deliver what users want, and they're on budget. Challenge means that it fails at one of those three, and successful means that they're and failure means that it fails at more than one of those three. Some people say that the Chaos Manifesto report is rather too negative, and one of the people that says that is Scott Ambler, who also collects data on software projects. And this is my organization of his data. The top line here shows iterative approaches to software development. The bottom line shows more linear, traditional kind of approaches. One of the things that amused me when I first saw it is if you make up your software development process on the spot, it's slightly more efficient than a traditional waterfall process. But joking apart, looking at these numbers, then the iterative approaches certainly have a stronger success rate than more planned approaches, and of these, lean tends to stand out from the others as a little bit more successful. So let's explore that in a bit more detail. So it's not really surprising, given my proclivity for wanting to apply a more scientific approach, the scientific method to software development, that lean appeals to me. And the reason for that is because when Edwards Deming came up with the ideas that led to lean thinking and lean production, he was also doing a direct lift of the scientific method and applying that to, in his case, manufacturing processes. So what's this about? This is really about delivering quickly. We want to be able to deliver in small batches. We want to make small changes and deliver those quickly. We want to have a focus on quality from the outset. We want to look at the whole process, and we want to optimize it in its entirety, not just pick convenient bits of it to look at. And we want to focus on eliminating waste. And there are a variety of different kinds of waste, including some things that at first thought may not seem like waste. So unnecessary variations are one particular case of form of waste. So if we do the same thing in different ways, then we're wasting time and energy and ultimately money in our ability to produce things. If we're working on too much stuff, if we're overburdened with work, that's also a form of waste. And interestingly, this goes fairly deeply into the mathematics of queuing theory, and you can apply this directly to teams. Teams taking on too much work will go slower as a result because they're spending all of their time trying to cope with the demands of work rather than having time to make themselves more efficient. Which kind of moves on to the next one, which is lean thinking is a lot about amplifying learning. We're looking to try and learn as a team and to improve ourselves in order to become more efficient over time. We want to make decisions late in the process because by deciding late, we're likely to have the best information. If we decide early in a process, then we're going to be guessing more, and we're more likely to make mistakes in our guesses. And we want to empower the team. We want the team that's doing the work to be able to see what's wrong with the things that they produce, so that they can react to those errors and correct them quickly and efficiently. They're going to be the best placed to be able to both spot the errors and to react to them and to correct them. Really what I'm talking about here is fundamentally about establishing feedback loops. And these feedback loops operate at a number of different scales in software development. These are just three that I've kind of pulled out, but there are many more than this when you start thinking about feedback as it applies to work in developing software. At the outside of the process is the feedback loop that I talked about, that vital feedback loop between from having an idea to getting useful software into the hands of our users and figuring out what they make of it. At the inside of the feedback loop is the classic TDD test cycle. We write a test, we see it fail, we write some code to make the test pass, we see it pass, we refactor, and then we check it in and we move on to the next thing. And these feedback loops give us an opportunity to work more effectively and work more efficiently, and to learn as we're going. At whatever scale they work, that's primarily what these feedback loops give us. As you can probably tell from the way that I've been describing this so far, I'm kind of a popular science nerd, and one of my heroes is this man, Richard Feynman. Richard Feynman is one of the finest minds of the 20th century. Feynman is a Nobel Prize-winning physicist, and he came up with the theory of quantum electrodynamics, which is the most accurate predictive tool that human beings have ever invented. Feynman was also kind of something of a philosopher on the subject of science, and a genuine first-class genius. And one of my favourite quotes of his is here: "It doesn't matter how intelligent you are, if you guess and that guess cannot be backed by experimental evidence, then it's still a guess." So if Feynman, a genuine genius, can't afford to guess, then I don't think we can either when we're developing software. Another vital tool in the approach to becoming more experimental in our approach, being able to become more scientific in our approach, is the use of cycle time. Cycle time is a really nice idea. It gives us a ruler for our processes that allow us to measure and improve over time. If you imagine the smallest change that you can make to your production system, and that change going through all of its normal validations, processes that it would go through in order to make sure that it was safe to put that change into production, how long would it take your organization to make such a change? And that's how we define cycle time. I'm going to show you two cycle times from two projects that I worked on. The first, I worked as a consultant for one of the UK's major banks, and their cycle time was 103 days. They couldn't make any change to their system in less than 103 days. If your cycle time is 103 days, you don't really have a feedback loop. After 103 days, if somebody comes to me and says, "Dave, your change broke production," I'm going to have no idea what that change was. I'm not going to know where it was. That change will have been part of a whole batch of other changes that went in that were developed over the period leading up to the 103 days, no doubt. And it's going to be very hard for me to figure out what actually went wrong and what the problem is and how I'm going to fix it. The second feedback loop is from another project that I worked on. This was actually a more complex software system than the first, significantly more complex. This was an automated low latency trading exchange, and we could make any change to that system and evaluate it fully and be prepared to release that change into production after 57 minutes. One of the changes, for example, that we made in that time was we decided to change database vendors. We didn't like the commercial contract that we had with our database vendor, so we switched to a different database. We ran the change through our testing system, and we got a couple of test failures. We fixed those test failures, we ran it through again, all of the tests passed, and we were ready to release that change. So it took us 2 lots of 57 in that case to make that change. I've worked in other organisations where just that project alone would have been a 6-month project with lots of people involved. If you've got a cycle time of 57 minutes, then you are going to know what happened. If somebody comes to me after 57 minutes and says, Dave, your change broke production, I'm going to know what I was doing 57 minutes ago. The change that I will have been pushing will have been small. The scope of the change that went out into production will have been small. It will be simpler to reason about. It will be easier to identify where the error was, and I will be able to fix it much more quickly. So what are we really talking about? So we're talking about this process of continuous delivery. So what's that really about? As a starting point, continuous delivery is the first principle of the Agile Manifesto. The Agile Manifesto says our highest priority is to satisfy the customer through early and continuous delivery of valuable software. That's a good starting point, and it's really what matters. It's really why we're employed. That we're not employed, those of us in the IT industry are not employed for any other reason than to provide software that's useful to our users. A good way of thinking about continuous delivery is to think of it as kind of a logical extension of continuous integration. Continuous integration is a great technique for development teams. It gives them really good feedback on the build system, and they'll be running some tests to figure out how well their software is doing. And it's a really powerful technique. But it doesn't go the whole way. So continuous delivery is taking that same idea and extending it for more of the software development process, not just covering the build of the system, but the provisioning, the deployment, into test environments, the provisioning and deployment into production environments, the management of change as it flows through from requirements into the development process. All of those things become part of the scope of continuous delivery process. I like to think of continuous delivery as a holistic approach to development. It really is about trying to get to a more repeatable approach to software development. A good kind of mental model for what we're describing when we talk about continuous delivery is that every time that you make a change that's destined for production, that gives birth to a release candidate. And the job of the rest of the continuous delivery process is to prove that that release candidate is not fit to make it into production. That's an important point, saying it that way around. That's another one of those lessons that we learn from science, that we can never prove that a release candidate is fit for production. We can never have enough tests to be absolutely certain that there isn't a problem. But if we have one failing test, we know that our system is not fit for production, and therefore we can stop it being releasable. We can prevent it from being released if a test fails. That idea of falsifiability is kind of a key attribute of a continuous delivery process. And the last point is finished means released into production. This list is taken from my book, Continuous Delivery, and actually, if I were writing that book today, I'd slightly reword that last point. Finished really means in production, in the hands of users, delivering value. Just deployed into production is not really finished. So here are some of the principles of continuous delivery. What we're trying to do is that we're trying to create a repeatable, reliable process for releasing software. The bad news is, if we want it to be repeatable and reliable, it kind of rules us out. Human beings are not very good at being repeatable and reliable. We're wonderful at lots of things, but repeatability and reliability aren't in the list of things that we're wonderful at. If we want it to be repeatable and reliable, it means that we need to automate almost everything. If we want to automate almost everything, it means that we've got to keep nearly everything under version control. we've got to have a great story. Excuse me. We've got to have a great story on version control, not just for our source code, but for the configuration of our systems, the definition, the specification of our the environments in which our application runs, the infrastructural code that our applications depend upon. All of those things need to be version controlled, as well as the source that we're creating. Software is an unusual thing in human experience. Mostly, if things are painful, it probably makes sense to avoid them as a human being. With software, that's a really bad idea, though. If something's difficult and we ignore it, it tends to get worse. If your release process is scary and problematic and causes lots of outages in production, then it's probably a bad idea to delay it, to take longer to do it. If you're releasing once every 6 months and you move to releasing once every 12 months, those problems are only going to get worse. If you're releasing every 6 months and it's painful, probably the best thing to do is to start releasing every 3 months, every month, every week, every day, every hour. In fact, working in a way so that your software is all permanently in a releasable state is really what continuous delivery is about. If you want to be able to do that, it means that we've got to have a good attitude towards quality. Our systems need to be deterministic. We need to be able to define precisely what we're releasing and when. We need to be able to, the behavior of our system needs to be deterministic so that when tests pass, it gives us confidence that the system is going to be working correctly. And that means we've got to have a very strong focus on quality. I've already mentioned that done means in the hands of our users delivering value. If you think about the release process, everybody kind of has a stake in it. Everybody's interested. The CEO is interested in when the software is going out. The business are interested. The support department's interested. Test parts of the organisation are interested. Operations personnel, developers, and so we want our processes and our technology to be transparent. We want people to be able to see the change that's flowing through the system and be able to see what's coming and when. And in order to do all of these things, this is not the kind of approach to software development that we can have a 6-month project and then we're done. This is actually a change in culture, and we need to adopt an approach to improving continuously. If you look at organizations that are skilled at this kind of process, they tend to be continually experimenting, not just with ideas and technology, but with the process that they're using, with the ways in which their teams are organized. Every aspect of their work, they'll be trying new things and finding out which things work and which things don't all of the time. This is just me being big-headed. This is a quote from Forrester Research from a couple of years ago, who said, if Agile software development was the opening act to a great performance, continuous delivery is the headliner. What we're talking about here is a sophisticated, a disciplined approach to software development that is really quite different to more traditional approaches. So what does this tend to look like when we see it in the wild? Well, organizations that work this way will tend to be noisy and collaborative. They tend to be you have lots of people discussing ideas all of the time, working closely together. You'll have information being broadcast to people and demonstrating where the process is. You tend to see lots of sticky notes stuck around. It tends to be data-driven. You tend to see there'll be lots of graphs and people looking at things. And we'll be looking and using those to evaluate how they're doing and measuring the success of their ideas. And they'll be looking to automate almost every aspect of the development process where they can. They tend not to do 2 things more than twice. First time is you're just trying to figure out what it is that you need to do. The second time is that you're rehearsing the automation, and the third time you'll be running the automation from then on. So let's walk through this process in a bit more detail. So we have some developers and they're working on some code and they think the code is good, so they'll probably run some tests locally, and then when they're all happy they're going to commit this to their version control system. That commit is going to trigger an evaluation of those changes, and we're going to see if those changes are good. So the commit stage is going to pick the changes from the source repository and evaluate them. This is classic continuous integration. This is nothing else so far. What's important about this process is that we want this feedback to be fast. We want the commit stage to give results as quickly as possible. I generally advise my clients to be looking, as a rule of thumb, to have an answer to any given commit in about 5 minutes. You should be trying to optimize the tests to have these tests in the commit stage should give a confidence that our change is going to be good, but they should give us a result very fast. If we want to have a high degree of confidence, it means we've got to run lots of tests. These are mostly the classic TDD style unit tests. We want these tests to be to give us very good coverage of our code and give us this result very quickly. That means that they can't afford to be talking to disk. They can't afford to be communicating across a network. They can't afford to be starting up a web server. They need to be local, in process with the code that they're testing, and faking everything else out. So in that scenario, you can run tens of thousands of these tests in just a few minutes and get a result very quickly. And that's what we're looking for. From now on, we start to diverge a little bit from just continuous integration. What we're interested in at the next stage is when the commit build, if the commit build is successful, we want it to create the releasable artifacts, that will be deployed into production. We don't want to have to rebuild the software again, because if we recompile later to deploy it into production, maybe we use a different version of the compiler. Maybe we link with different libraries. Maybe those changes introduce an error that would have been caught by one of the tests that we're running in the commit stage. What we want as an output from a successful commit stage is we want the stuff that is going to be deployed into production, and that stuff, precisely that stuff. So we're going to generate deployable artifacts that will be releasable into production, and we're going to store those in something called an artifact repository. At this point, the developers can now move on to work on something new. The commit stage has given them a result in 5 minutes or so, and they can move on to thinking about something else. Now, there are few stronger advocates for test-driven development and unit testing than me. I think it's a wonderful tool, excuse me, in the software development arsenal. But what test-driven development does, and what unit tests do, is they assert that the code does what the developer thinks the code should be doing. That's not necessarily the same thing as asserting that the code does what the users want it to do. And so for that, we need a different kind of test. In continuous delivery circles, we call these acceptance tests. And the job of acceptance tests is to evaluate changes in lifelike circumstances from the perspective of an external user of the system in production-like test environments. Acceptance tests are going to be slower because we're going to be running them in lifelike circumstances, in production-like test environments. So at a minimum, we're going to have to start the system up at least once and shut it down at least once in order to run some of these tests. That's usually relatively slow compared to the time to run a unit test, which is in milliseconds or microseconds. And so the acceptance tests, we're going to have fewer of these things, and they're going to run more slowly, but they're going to be more lifelike in terms of the interactions with the system. The acceptance tests run on a cycle, and the acceptance test, when the acceptance test environment becomes free, it will look into the artifact repository and figure out which is the newest successful commit build, potentially jumping over other commits. We don't want to evaluate every single commit at the acceptance test stage, because otherwise we'd have an ever-growing queue of builds to process. So we're going to jump over those, which means that if something breaks at this point, it may have been caused by a number of different commits, potentially. The acceptance test will run, and they will report back the results, and they will tag the release candidate that's stored inside the artifact repository with the results of that run. I mentioned earlier that human beings aren't very good at repeatable, reliable stuff, and we want to automate nearly everything. But human beings are wonderful at other things. Human beings are wonderful at kind of the fuzzy pattern matching. Human beings are going to find things like, if I write a web page with a blue button with blue text which you can't read, then an automated test is going to be perfectly happily just push that button. A human being is going to realize that you can't read the text on the button and report it as an error. Human beings are going to perceive different things, and so it's useful to have some level of human interaction. One of the things that's happening at the point at which we deploy to the acceptance test, this is the first time when we're probably going to execute our deployment automation. And we want the deployment system that we use to be the same deployment system that we will use if this release candidate makes it into production. So at the point at which our automation deploys a release candidate into the acceptance test environment, we'll be using that deployment automation to set up the system and get that release candidate up and running in the test environment. Similarly, when our tester wants to run a release candidate in a manual test environment, they should be using the same deployment mechanisms and provide you with those. We probably don't want to waste a human being's time, an expensive human being's time, on code that hasn't passed acceptance testing. So we probably only want to make those release candidates visible to the human being that have passed acceptance testing, so that we're not wasting their time on something that the automation can tell us is broken. Again, if once the testing is complete, we can collect the results of that, and we can tag the release candidate in the artifact repository. The system that this particular deployment pipeline is based on was a very high performance trading system. We took performance very seriously, and so we divided the performance testing up into two different stages. We did component level performance testing for performance critical components of the system, and we did system level performance for whole system, more lifelike testing. You can kind of think of these as the performance equivalent of commit and acceptance tests to some degree. The component level tests would drive, say, our matching engine at a certain level, and it would fail if we couldn't process a certain number of matches per second. The system level performance testing would replay production-like scenarios at scale against a lifelike deployment of the system in software that was configured in exactly the same way as our production hardware. You can see that our release candidate is kind of, as it progresses through this series of tests, both manual and automated, what's happening is that we're gaining increasing confidence in the viability of this release candidate, in its releasability. One thing that we don't know yet is this release candidate going to work with production data? We want to be able to modify and basically get wrong the design of our data structures, as well as get wrong anything else wrong, and be able to recover from such a mistake. So we want to be able to migrate our data. We want to be able to move it and change it. So in the system that this example was based upon, we would we would take a cut of our production data, we would deploy that using our automated deployment tools into our testing environment, and we would, at the point at which our deployment automation deployed a new release candidate, it would upgrade the data set to new version, using data migration techniques to move the data into new schemas or whatever was required for the change. Finally, we want to release into production, and again, we want to be able to only provide release candidates that have passed a certain threshold. In this case, we don't want any release candidates that have failed any test. So any failure in any of these stages will have rejected that release candidate, and so that release candidate will simply not be visible as a deployable thing to the person that's going to make the decision to release into production. In our case, this was a finance system, and so we had regulatory requirements that required us to have a human being, actually 2 human beings that would agree to release any particular change into production, and so we built that into our automation too. So we had to have the authorization of 2 individuals before a release candidate was released into production. And again, we capture the metadata, we capture the fact that this release candidate has made it into production. This automated process is referred to as a deployment pipeline, and the deployment pipeline is a key idea in continuous delivery. Fundamentally, what a deployment pipeline is, though, is something fairly simple. It's a branch prediction algorithm. What's happening is that at the point at which the developers commit the change to the source repository, they're taking a bet. They're betting that if the commit build passes, then they're good to go. Their change is good, and it's most likely going to pass all of the rest of the tests. They can then move on to working on something else. If a test fails later in the process, it's still their responsibility to act immediately and to fix that test, but they've lost their bet. Now they've got to drop what they were working on, they've got to switch back into the context of the change, they've got to figure out what the change was. Their change is going to be maybe bundled in with other people's change, it's going to be more complex to figure out what it is, but still they're going to be relatively close to it. If the cycle time here is in the order of an hour or so, 57 minutes in the case of the example that this was taken from, then they're going to still remember what the change was, and they're going to be in a reasonably good position to be able to fix it. But they've still lost their gamble. If, on the other hand, all of the rest of the tests pass, they've worked in parallel with that, and they've been working on other things, and so they won their gamble. The other thing that I would like to point out from this diagram is, if you just pause for a minute and think what it takes to implement a system like this. It's not really possible to implement a system like this without having, almost by accident, full traceability of every change that flows into production. This is a regulator's dream. This is what compliance organizations really want. I've spent a number of years working in regulated industries, and although often when you first describe the idea of releasing frequently to regulators, they are somewhat wary, to say the least. Actually, when you describe the process, they think it's kind of the gold standard for what they're looking for. This is very good fit with heavily regulated organizations. One of the pushbacks that I sometimes get for this is, okay, so that all sounds that sounds great, and it probably works fine for small projects, but it can't possibly scale. My answer to that is the Google build process. Google made the somewhat unusual decision of storing all of their software in a single monolithic repository. That's not absolutely true. There are a few projects that are outside, but the vast majority of Google's software is in a single repository. They run more than 60 million builds per year, and that number is growing exponentially. They process more than 100 million lines of code in this single repository. Tests are run on every single commit, and there are more than 20 commits per minute. There are more than 100 million test cases executed every day. So if your build is larger than that, maybe it doesn't scale, but so far the data is with me in that it does scale. The other pushback that I sometimes see is this process is too risky. My software releases are very scary events, and I couldn't possibly release as frequently as you suggest. My answer to that is the Amazon build process. For Amazon, the mean time between deployment is 11.6 seconds. They are releasing changes on average once every 11.6 seconds. Each of those changes, on average, is deployed to more than 10,000 hosts. Since adopting this approach, they've seen a 75% reduction in outages triggered by deployments. They've seen a 90% reduction in the time spent recovering from problems, and less than 1 in 1,000 deployments cause any problem, any outage at all. They have instant feed rollback and instantaneous rollback, and the reduction in complexity because of the automation that you have to apply to get these sorts of numbers. Another feedback that I sometimes work is, okay, well that's fine for the web companies. It's good for them, it's easy for them to work, but my technology is too complex. My answer to that is the HP Laserjet firmware team. So their experience was a very interesting one. Some years ago, they were in a very difficult position. They got to such a state with their software development process that the business had literally stopped asking for new features. They had I think it was a 5-year backlog of features, and they weren't processing anything. They reckoned that they were spending 5% of their global development efforts on what they called innovation, which we would call just any new stuff. Any new development at all was only 5% of their total development effort. If you look at the breakdown of the things that they were spending time on the left-hand panel here, it's kind of interesting. So they spent 25% of their global development effort, 5 times as much effort as doing new things, on porting code. That's because they had a single repository for a single version, notionally, of their firmware, but they had a branch for each Laserjet device. And so if you introduced a new feature, you then had to go and port that to every other branch for every other device in the version control system. They spent 25% of their effort on product support, which suggests that they had a quality problem as well, and 15% on manual testing. After the change, after adopting continuous delivery as an approach, the distribution of work changed. They were doing very different things. They are spending an awful lot of time writing tests, automated testing, working on continuous integration. There's a significant chunk of their time that they spend doing those things. But the bottom line is they now spent 40% of their development effort doing new things, and nearly 10 times improvement. Overall, they've seen their development costs reduce by 40%, the programs under development increase by 140%, development costs per program down by 70%, and resources now driving innovation increased by a factor of 5. This is documented in this excellent book, which I recommend to you, called A Practical Approach to Large-Scale Agile Development, from one of the managers from the team. It's not a deeply technical book, but it is an interesting book that describes making change in existing organizations and the approach that HP took to adopting some of these ideas. It's my argument that continuous delivery changes the economics for software delivery, and increasingly we're getting real data to back up my argument. In a recent survey, 80%, 87% of companies whose development and operations functions were rated excellent saw revenue growth of more than 10% in 2013. And 2013 wasn't a very good year economically, globally, so 10% wasn't bad at all. In contrast, 13% of companies whose development and operations were rated average or worse saw similar growth. There's a bottom line advantage to doing this kind of work, working in this way. You see lower failures, higher reliability of systems, higher quality, and the development teams that work in these organizations enjoy it more. And so organizations that work this way attract higher quality developers and retain them for longer. It's my argument that continuous delivery is going to affect your organization. Either you will be starting to do it yourselves, or your competitors will start to do it, and they will start to overtake you when they do, because it's an effective way of developing software. So who does this? Many of the organizations that you'd expect, the big web organizations, Facebook, Amazon, Google, Netflix, those sorts of organizations, but also some organizations that maybe you wouldn't expect. So the New York Times, ING, the Dutch bank, have made a huge investment in continuous delivery and are seeing enormous advantages from doing so. SAP, I confess, to my mind, SAP were kind of the definition of legacy systems, but they have groups talking about parts of their organizations that are practicing continuous delivery and seeing very significant advantages to doing it. The New York Stock Exchange. Continuous delivery changes the economics of software development. It's a more effective approach to doing these things. That's the end of my presentation. Thank you for your time. I'm more than happy to take questions there. So I have a question here from Greg saying, can you provide any examples of quick wins on undertaking a task of moving from traditional to a continuous delivery model? Are things we can look to change initially that are relatively painless, quick to provide good returns? I think a lot depends on the nature of the organization, the problem that it's facing. The picture that I've painted is of a reasonably complex, holistic approach. The good news is that you don't have to have all of that in place before seeing benefits. So each of the steps along the way is an advantage. If your organization is not yet using source control, and surprisingly some organizations still don't use source control, but if you're not source controlling your systems, then introducing source control is a step forward. Continuous integration is a big step forward. Working iteratively is a big step forward. Working with smaller teams and more collaborative teams is a big step forward. The introduction of automated testing, all of these things, the way in which you process requirements, it varies a lot by organization. I think that perhaps the most common two approaches that I generally recommend to clients are first, I recommend that you do a breakdown of your cycle time, the kind of value stream analysis that I was showing earlier. Let me see if I can just find the slide. So if you can kind of look at your own process and do a map of it like this and figure out where the time goes and just look to optimize that. One of the wonderful things about cycle time and the experimental iterative approach is that combined they kind of drive out all of these good behaviors. So if you start by measuring your cycle time and then just optimizing to reduce it, to work in a way so your software is always in a releasable state, in a reasonable amount of time, then that will drive good behaviors. You can't have a short cycle time without good automation. You can't have a good cycle time without good configuration management. You can't have a good cycle time without collaborative teams and automated testing and all of this other good stuff. So it's a really good tool for driving that. So that's a great place to start. The other place to start from a technical point of view is continuous integration. And for any build team, just being able, if you don't have continuous integration, just being able to build your system on demand on a repeated basis is a step forward. Then being able to build it and run some tests against it is a huge advantage, and that will grow in impact over time. So I think those are probably the most important starting points for organisations that are working in more traditional modes. I can't currently see any more questions on the list.
Great. Well, I think that's all of the questions for today, Dave. So thank you once again for a great presentation. And to everyone, we have made the session recorded, so we will be sending out the presentation and Dave's slides tomorrow. So you'll receive those very shortly. Thank you very much, everyone.
Thank you.